Good evening. My name is Yuvraj, and in today's session, we are going to discuss about CPU, how our code works on CPU, how the other programs work, and what is the internal working of the CPU. This is going to be more of a theoretical session, and we'll begin with the basics. So let's begin. So the central processing unit of a computer is in charge of all computations. The first mass-produced CPU was the Intel 4004, designed in the late 60s. It was a 4-bit architecture and it had far less complexities than the 64-bit systems that we use today. The CPU can only process binary data, that is zeros and ones. So it takes in a byte or two to represent what instruction is being run, followed by whatever data is required to run that instruction. Now, there is something called assembly language. This is basically easier for us to understand and write to. So whenever we want CPU to perform some operations, we cannot just put zeros and ones because it would be very difficult and complex for us to do that, and so that is why we have assembly language. Anyways, when we need the CPU to run certain processes, the assembly language must be converted into the binary data, that is 0 and 1. Now, let us talk about RAM. RAM is our computer's main memory bank, a large multi-purpose space which stores all the data used by the program running on our computer. So it includes the program code as well as the code at the core of the operating system. It always so whenever CPU performs certain operation, it has to read from the RAM, and if the code is not loaded into RAM, CPU cannot perform the operation. So it is very important that the code is there in the RAM. How exactly does CPU read from the RAM is something called fetch and execute cycle. The CPU stores an instruction pointer which points to a location in RAM from where it is going to fetch the next instruction. So as soon as it executes an instruction, the instruction pointer moves and carries on with the process, that is fetches another instruction and executes that. This is what we call as fetch and execute cycle. So it reads instruction from the memory at the current instruction pointer, then executes it, runs the instruction, and then moves the instruction pointer again. So when we have our conditional statements in our program, like the if and else statement, so it moves the instruction pointer to a particular location in RAM, which specifies the condition to be run at that condition. The instruction pointer, this instruction pointer is stored in something called as a register. So registers are small storage buckets that are extremely fast for the CPU to read and write to. Each each CPU architecture has a fixed set of registers which are used for everything from storing temporary values during computations to configuring the processor. However, this concept raises several questions about if CPU performs one task at a time and then moves to the next task, then how are we able to multitask? Like, for example, we are able to browse some article on the web page at the same time we can have YouTube running on our background, or any music running on the background. How is it able to multitask? Secondly, if it is able to execute the statements or the instructions sequentially, then why does it not get stuck inside whatever program it's running? So we'll be answering these questions in our session. Now we'll look at what is a kernel. So our computer's operating system, like Mac OS, Windows or Linux, is a collection of software that runs on our computer and makes all the basic stuff work. I mean, by basic stuff, I mean apps, fonts, icons, and so the kernel, however, is the core of the operating system. This The kernel has nearly full access to our computer's memory, peripherals, and other resources, and is in charge of running software installed on our computer, known as user-land programs. So, for example, Linux is just a kernel and needs plenty of user-land software like shells and display servers to be usable. The kernel in Mac was called XNU, and this is just for reference, and the modern Windows kernel is called NT. Now we'll see something called the modes or the privilege level in a processor. The privilege level or the ring gives the processor the control over what it is allowed to do and what it is not allowed to do. In modern architectures, we have at least two options. One is the kernel or the supervisor mode, and the other is the user mode. Now, these like in modern architectures, these are very common, so it will be there. In kernel mode, the CPU is allowed to execute any supported instruction and has almost full access to the memory. However, in the user mode, only a subset of instruction is allowed. Input and access to some of the memory is limited. Many of the CPU settings are locked, and this is because we cannot trust an application to gain complete control over our input, output, and memory access of our system. So generally, the drivers run in kernel mode and the applications run in the user mode. So whenever we execute a program, the kernel initiates switch to user mode. So let us take an example here how the processor modes manifest in real architectures. On a 8664 system or the architecture, the CPL, I mean the current privilege level, can be read from a register called CS or the code segment. To be very specific, the CPL is contained in the two least significant bits of the CS register. Now, what do I mean by this? There will be certain binary values. The last two binary values or the least significant binary values will decide the uh, privilege level. So on this system, I mean the 8664, there are four possible rings. This is because we can have four combinations of zeros and one, which can be 00, 01, 10, and 11. So the ring 0 is referred to as the kernel mode, and ring 3 is referred to as user mode. Now ring 1 and 2 are designed for running drivers, but are used by only a handful of operating systems. Now we shall move on to syscall. So the programs that run user mode, uh, they run in user mode because they cannot be trusted with the full access to our computer's resources. Like the some memory is limited, some CPU settings are locked, and output and input is restricted. But these programs need to be able to access input, output, allocate memory, and interact with the operating system somehow. And for this purpose, we need software interrupts. Or software interrupts are basically a way to ask the system, the kernel, or the OS for help. So if you guys have ever written code that interacts with the OS, you will probably know functions like open, read, and exit. Below a couple of layer of abstractions, all of these functions, all these type of functions use system calls to ask the OS for help. A system call is a procedure which lets a program start a transition from the user space to the kernel space, jumping from the program's code into OS code. User space to kernel space transfers are taken place using a processor feature called software interrupts. Now, during the boot process, the operating system stores a table called an interrupt vector table. This is stored in the RAM and is registered with the CPU. The IVT maps interrupt numbers to handle code pointers. Just for a fact, in 8664 architecture, this is called an interrupt descriptor table. After this, the user line programs can use instructions like INT. INT is basically an instruction, how do I say, the process, a procedure, an instruction procedure, which will tell the processor to look up the interrupt number in the IVT and then switch to kernel mode and then jump the instruction pointer to the memory address stored in the IVT. When the kernel code finishes, a similar instruction to INT called IRET is used, which basically is tells the CPU to switch back to user mode and also returns the instruction pointer to where it was before the interrupt was triggered. So let me summarize. We know that user mode programs can't be trusted with the full access to our kernel, but they need to interact with our OS, and this can be done with the help of system calls and procedures like INT and IRET. Now, programs need to pass data to operating systems when triggering a syscall. OS needs to know which specific system call to execute alongside any data the system call itself needs. For example, what file name to open. The mechanism for passing such information will vary from one operating system to other to some other architectures. So, but it is usually done by placing data in certain registers or on stack before triggering the interrupt. But this would get a very big problem for programmers because we cannot expect anyone to drop down to assembly language anytime they want to allocate memory or read a file. It would be very impractical. It would be very impractical. So for this, operating system provides an abstraction layer on top of these interrupts. There are certain high-level library functions that wrap the necessary assembly instructions, and these are provided by libc on Unix-like systems, and for Windows there's something for Windows as well. Call to these library functions themselves does not cause the switch to kernel mode. These are just standard library function calls. Inside these functions or the libraries, assembly code does actually transfer control to the kernel, but it is a lot more dependent on the platform rather than the wrapping library subroutine. So we have an example here. Whenever we call an exit one from C running on a Unix-like system, that function is internally running machine code to trigger an interrupt after placing the system calls code and arguments in the right registers or stack, whatever we discussed, where it is usually placed, where the information is usually placed. Now we are going to look at hardware interrupts and why are they required. We have already discussed software interrupts, how they hand control from a user land program to the OS. These are called software interrupts because they are voluntarily triggered by the program machine code executed by the processor in a normal fetch and execute cycle where it tells to switch to kernel mode. Now, when we are talking about hardware interrupts, the OS scheduler uses timer chips like PITs to trigger an hardware interrupts for multitasking. So, before jumping to the program code, the OS sets the timer chip to trigger an interrupt after a certain period of time. The OS switches to user mode and jumps to the next instruction of the program. When the timer elapses, it triggers an hardware interrupt to switch to kernel mode and jump to OS code. The OS can now save where the left off and load a different program and repeat the process. This is called preemptive multitasking. The interruption of a process is called preemption. Uh, the best example of this would be, I think I've already given this example, browsing an article on a web page and listening to the music at the same time. So now let's talk about time slice. Uh, a time slice is basically the duration an OS scheduler allows a process to run before preempting it. The simplest way to pick time slices is to give each process the same time slice, perhaps in the 10 millisecond range, and cycle through tasks in order. This is referred to as fixed time slice round robin scheduling. This is not a very efficient way. However, a slight improvement in this could be using target latency. Target latency is the time it takes for a process to resume execution after being preempted, assuming a reasonable number of processes. So, time slices are calculated by dividing target latency by the total number of tasks. This is better than the previous the fixed time scheduling because it eliminates wasteful task switching with fewer process. And let us consider an example with a target latency of 15 milliseconds and 10 processes. Each process would get around 1.5 milliseconds to run. With only 3 processes, each process gets a longer 5 millisecond time slice while hitting the target latency. This switching process is computationally expensive because it requires saving the entire state of the current program and restoring a different one. After a certain point, if we take a very small time slice, it will result in performance problems because the processes will switch very rapidly, and it is common to give time slice duration a lower bound, which we refer to as minimum granularity. This does mean that the target latency is exceeded when there are enough processes for the minimum granularity to take effect. Now, round robin scheduling with this basic time slice calculation is close to what most computers do nowadays. Since 2007, Linux had used a scheduler called CFS. So you can refer this diagram for easy understanding of the dynamic round robin scheduling. Now we shall talk about kernel preemptibility. So the kernel code might make programs feel laggy if it takes too long to handle a syscall. So modern kernels, including Linux, are preemptive kernels. This means they are programmed in a way that allows kernel code itself to be interrupted and scheduled just like user land processes. So that's about it for uh, multitasking and preemption. Now we are going to look at Linux kernel to figure out how programs are loaded and run in the first place. Uh, so some of you may ask, why only Linux? First of all, it is open source, so easy to get things various kind of informations about it is easily available on the internet to read. So let us start with a very important system called execve. Now this what it does is it loads a program, and if that is successful, it will replace the current process with that program. A couple of other syscalls such as exec VPE, exec CLP exist, but they all are built on top of exec VE in various fashions. So we are now going to see the call signature, or how exec VE looks. Uh, so here you can have a look at the call signature of exec VE. We can see that three arguments are passed here: file name, argument, and the RV and the ENVP. So the file name argument specifies the paths to the program to run. RV is a null terminated list of arguments of the program. By default, the first element of this list is the file name of RV. The envp argument contains another null terminated list of environment variables which are used as context for the application. These are essentially key value pairs. Now let us see how execv is defined. So we can see here how it is defined. So it returns a do execv function, which in turn has its first argument as the get name, where the file name has been passed. So get name is a function where we have passed the file name. So what it exactly does is it copies the string from user space to kernel space and does some usage tracking things, and then returns a file name struct. The structure of that file name I will show you in a second. This is how the structure of a file name looks like. So it stores a pointer to the original string in user space, as well as a new pointer to the value copied in the kernel space. So the execv system call then calls a do execv function. This in turn calls a do execvat common with some defaults. Now we are going to look at do execvat structure. We shall now discuss what a file descriptor is. A file descriptor is a type of ID that points to some resource. Here we can see in the last line, do execvat common, a file descriptor is passed. This basically specifies the directory to execute the program relative to. In execv, a special value, a similar kind of file descriptor is used. The argument is called @_fdcwd. Not really important. Now we'll move on to do execvat common. This is the core function handling program execution. Uh, we have now reached do execvat common, the core function handling program execution. Now we'll not look at the code for this. We'll look at what this function actually does. The first major job of do execvat common is setting up a structure called Linux binary program. Uh, so data structures like mmstruct, VM area struct are defined to prepare virtual memory management for the new program. argc and environment C, envc, are calculated and stored to be passed to the program. File name and inter store the file name of the program and its interpreter respectively, as the name suggests. These start equal to each other but can change in some cases. One such case is when running interpreted scripts with a shebang. Now, what is a shebang? So basically, it's a special line at the beginning of a script that tells the OS or the operating system which interpreter to use when executing the script. So that is what a shebang is. So when executing a Python program, for example, a file name points to some source file, but interpreter is the path to the Python interpreter. Now we'll talk buff. Buff is an array filled with the first 256 bytes of the file to be executed. It is used to detect the format of the file and load script shebangs. First of all, as already discussed, the Linux binary program which contains the buffer. The buffer contains the first 256 bits, the first 256 bytes of the program that is to be run, and that contains the information about the file format. So now the next major job of the kernel is to iterate through a bunch of binary format handlers, and these handlers are defined in files like these. Kernel modules can also add their own binary format handlers. Now what it does, that it will take that load binary function, which takes a Linux binary program struct and checks if the handler understands the program format. Just now I told that the first 256 bits of the buffer contains the format of the file. So if so the function will check if the extension is matching or not, if the handler supports the format or not, and if and if it supports, then it will prepare the program for execution and return a success code. Otherwise, it will quit and return an error code. So the kernel tries the load binary function of each binary format until it reaches one that succeeds. Now we will discuss about memory management unit, or the MMU. So it turns out that when the CPU reads from or writes to memory address, it is not actually referring to a physical memory. Rather, it is pointing to a location in virtual memory space. The CPU talks to a chip called memory management unit, or the MMU. This MMU works like a translator with a dictionary that translates location in virtual memory to locations in the physical locations in the RAM. So when the CPU is given an instruction to read from a particular space, to read from a particular memory address, uh, it provides this address to the MMU. The MMU looks up in its own dictionary and matches it with a physical address. Then returns this physical address to the CPU, and that is after that the CPU reads from that physical address. When the computer first boots up, memory access directly go to the physical RAM. Immediately after startup, the OS creates translation dictionary and tells the CPU to start using the MMU. This dictionary is what we call the page table, and this whole process of translating from the virtual memory to the physical addresses is called paging. Entries in the page table are called pages, and each one represents how a certain chunk of virtual memory maps to certain physical addresses in the RAM. These chunks are always the fixed size, and it differs. The chunk size differs from processor architecture. For example, the 8664 has a default 4 kilobyte size, meaning that the page specifies the mapping for a block of memory which is 4096 bytes long. However, okay, so we can see the address breakdown of the paging here. The lowest 12 bits will always be the same, after and before the MMU translation. This is because the amount of bits needed to index the 4 kilobyte page, uh, because we need to because these bits are needed to index the 4 kilobyte page that we get post translation. Now this 8664 also allows operating systems to enable larger page sizes. This having a larger page size can improve the translation speed. So it improves the translation speed but also increases the memory fragmentation and waste. Because the larger the page size, the smaller the portion of the address has to be translated by the MMU. The page table itself resides in the RAM. While it contains millions of entries, these entries are a size have a very small size, are confined to a couple of bytes. So, to enable paging at boot, the kernel first constructs the page table in RAM. Then it stores the physical address of the start of the page table in a register called page table base register (PTBR). Finally, the kernel enables paging to translate all memory access to the with the MMU. On a 8664, the top 20 bits of control register 3 or the CR3, they function as the PTBR. Bit 31 of the CR0, designated PG for paging, is set to 1 to enable paging. I hope that is clear. That the first 20 bits of the CR3 or the control register 3, they function as the PTBR, which we have already discussed. One interesting thing about this paging system is that it can be edited while the computer is running. This is how each process can have its own isolated memory space. When the OS switches context from one process to another, an important task is to remap the virtual memory space to a different area in the physical memory. Let us say we have two processes, process A and some process B. Process A has its own code and data, and process B can access its code and data from the very same address. Those two processes can be even uh, be same instances of a same program. Sorry, be instances of the same program, because they aren't actually fighting over that address range. The data for the process A is somewhere far from process B in physical memory, and is mapped to the same virtual memory address. So this is how it happens. It is happening while your computer is already running. So let's talk about security with paging. The process isolation enabled by memory paging improves the code ergonomics, but it also creates a level of security. Uh, the processes cannot access memory from other processes. This answers our question which we had in the beginning, that if the programs run on the CPU and CPU can access RAM, why can't code access memory from other processes? So first things first, the kernel obviously needs to store a plenty of data of its own to keep track of all the processes running and even the page table itself. Uh, every time a hardware interrupt, software interrupt, or a system call is triggered and the CPU enters the kernel mode, the kernel code needs to access that memory somehow. Linux solution is to always allocate the top half of the virtual memory space to the kernel. So Linux is called the higher half kernel. Windows employs a similar technique. Uh, it would be terrible for security if user-land processes could read or write kernel memory though. So paging enables a second layer of security. Each page must specify permission flags. So one flag determines whether the region is writable or it can be only read, or it is readable. So another flag tells the CPU that only kernel mode is allowed to access the region's memory. This latter flag is also used to protect the entire half kernel space, higher half kernel space. The entire kernel memory space is actually available in the memory mapping for the user space programs. They just don't have the permission to access it. The page table itself is actually contained within the kernel memory space. When the timer chip triggers a hardware interrupt for the process switching, the CPU switches the privilege level to the kernel mode and jumps to Linux kernel code. Being in the kernel mode, that is the ring 0 that we discussed in the privilege level thing, allows the CPU to access the kernel protected memory region. Now this kernel can write to page table, which resides in the upper half of the memory, to remap the lower half of the virtual memory for the new process. When the kernel switches to the new process and the CPU enters user mode, it can no longer access any of the kernel memory. So that's about it for this session. And thank you for watching this. If you guys have any queries, you can post it in the comments and let me know. Thank you. Thank you very much.